Okay, perfect. Can everybody, the 755 lab is the lab you need to do on campus in the lab. Can you pop up, you can just send it to everybody. When are you going to the lab? Just everybody pop up what day you're currently planning to go to the lab to get that 755 done. Friday. Okay, so Tuesday next week, Francisco. Okay. Friday. Everybody else? When are you going? You can't go to lab on Sunday. Lab's not open on Sunday. What day is, let's see. So that's this Saturday, Pedro? Okay. Because remember, this lab is due next week. And I'm not going to extend it because 2 weeks is more than enough time to get into lab. Okay. So please make sure you do your lab commands like what we talked about. And I want you to practice using the lab commands. Again, I know right now this is a super short lab, but it's better to cut your teeth on a little short lab than a longer, harder lab, okay? Okay. So let me see here. Okay, let me share my screen. All right, so I know that online learning isn't the easiest, right? I know that it's probably a little better because we're doing live online, and I'm so entertaining that I know that it makes it better than having a boring old teacher just talk at you like a talking, I could just talk like a talking head, Ethernet straight through both ends, T568A. Okay, one of the ways to make online learning and live online learning better for you and more rewarding for you and me is you need to take notes and be engaged, right? So that's one of the reasons I'm always making you answer questions, because I know that it's easy. I mean, like even for me, I leave my cell phone on. I don't normally, but because sometimes you guys are sending me text messages off and on too. So I know it's easy to get distracted. But what I really want to avoid is I want you guys to really be engaged as much as possible in the class, not surfing YouTube, not surfing the internet. And so when I say write this down, I mean write this down. Okay? It's important. Also, sometimes what you want to do too is just have your notes that you already took from the last class and from our reading material, right? Because I make you all take notes. And sometimes you can just make notes on that as we talk about things, because I'm trying to highlight and bring to mind stuff that I know you might be facing on the CCNA. So one way, again, just to stay engaged with this live online is taking notes, writing stuff down, participating in online. So I just want to encourage you again, we're just finishing week 4. Normally this class is only an 8-week class, if you can imagine. So we're really lucky because this is a 10-week class, so we still have 6 weeks left. So plenty of time for us to just really get in and take advantage of this. So again, I just want to really encourage everybody to advance your online learning skills. It's really hard. I mean, COVID has made this challenging, you know, in the online learning environment. So I just want to really encourage you to be an active participant in your learning, because that's the way to get better at this stuff. Okay? Okay, so let's just review. Okay, because one of the things you're going to do when you set up that lab, when you go to campus, is I want to make sure you're using the right cables. And we talked about this, I think, did we talk about this on Monday? Gosh, it seems so long ago already, but we talked about crossovers and we talked about straight throughs and the way that the cables are pinned out, right? So there's two different heads, the T568A and the T568B. Well, the A's, they start with green and the B's start with orange. So when you go to lab and you're cabling up your 7.5.5 lab, if you can remember to look at the pins, look at the ends of the cables, and just take a look and see what you're doing. Like if we were in class, I'd have it and we'd pass one around and we'd look, but we're not in class, so I can't really pass one around and have you take a look. So just make a little note to yourself, if you could remember when you're cabling up your network, take a look at your cable. Okay, so a straight through, when would I use a straight through? You've got to be a little bit more specific than just connecting to a device. Yeah, so I've got a lot of answers. So it's when we're connecting two different devices, right? So if I'm going to connect a computer to a switch, if I'm going to connect a switch to a router. Now, when do I use a crossover cable? If I'm connecting two devices that are the same, right? Two devices that are the same. So what makes a straight through is that both ends are exactly the same. So if I look at the end and I have one that starts with a green, and I look at the other end and it starts with a green, that's a straight through. Two T568 A's and an A. Also, if I look at an end and it starts with an orange, and this one starts with an orange, that's also a straight through. It means that the cables run straight through, okay? They run straight through. A crossover means I have one end that starts with a green and another end that starts with an orange, because they've been crossed over on one end, okay? They've been crossed over. So here's a trick question that we talked about whenever we talked about this stuff. If I want to connect a PC directly to a router, or maybe a server directly to a router, am I going to use a crossover or am I going to use a straight through? Yeah. Okay, so can somebody come on and tell me why you're choosing a crossover? Because like intuitively, I'm thinking a PC and a router, they're not really the same. Why would I use a crossover? But you guys are right, you're going to use a crossover. So someone unmute yourselves and explain to me why we are going to use a crossover.
We would use a crossover because the wires of both are the same. So like a PC would have the same kind of like brain as a router would. So that's
Right.
why there would be a crossover.
Exactly right. So if you think about where you plug the cable into your computer, like even if laptop, right, you can wire your laptop up to an Ethernet cable. Um, the NIC card, so where you plug your Ethernet cable into on the router and where you plug it into your computer, their brains or their wiring inside that card are the same. So as far as a PC and a router are concerned, they're similar. They think alike. They think alike. Okay, so now we also talked about a console cable or a rollover cable. So what does a rollover cable look like? What does a console cable look like? Somebody come on and give me a description of how you would maybe describe that. Anybody? So it's a rollover cable. So remember, it's rolled over, right? They run straight through, but they just are the exact mirror image on each pin. A rollover cable. That's how the console cables are wired. They're a mirror image. The pins, if you're looking at them, they're a mirror image. Okay. Okay, we are going to be talking about layer 2. So remember, the way that the book is set up is that we move through the layers. So Ethernet cables, radio frequency, the media is all at layer 1, the physical layer. So now we are moving to layer 2. Now, there is a device that is associated with layer 2. What is the device associated with layer 2?
Oh my god. Oh shoot. Oops, my bad. Sorry.
That's okay. A switch, right? At layer 2 is the switch. Layer 2 is the switch. And MAC addressing happens at layer 2. You're absolutely right. So at layer 2 is the switch. Now, if we think about the physical layer, our computer, where the NIC card is, that's actually layer 1, right? The actual NIC card is layer 1. And then we're going to start to move our data onto the switch, right? In our home routers have a little switching mechanism built into them. That's why we don't have to have a switch and a router. Home routers are built kind of like combination devices, okay? So at the layer 2, we have the MAC address. We have the MAC address. Now, if I needed to look up my own MAC address, how could I do that?
You'd go into the CMD and
Yeah.
type in IP config.
Absolutely. You have to include the all because the IP config will just give you the IP address, the subnet mask, and the default gateway, but IP config all will give you the MAC address as well. And why is there a MAC address on layer 2? What is the MAC address used for? How do our devices use a MAC address? Let's see. Alondra, can you answer? How our devices use a MAC address? Oh, is Alondra not on? Oh, I don't see Alondra. Okay. Let's see. Francisco, can you answer? MAC addresses are used to forward traffic to a specific device and to identify the device. Okay, but what does that mean? Like, tell me what that means. Do you know what that means? Forwards traffic to it, like who, where? I know it says device, but not routers and, I mean, kind of routers and switches. So a MAC address, okay, again, you guys need to write this down and understand it because, like, I can see, right, the MAC address is used to forward traffic to a specific device and to identify devices, but you need to make sure you know what that means too. I'm not saying you don't know what that means, but you need to make sure. MAC addresses are used for devices that are on the same network, the same local connection. Okay, so if you could imagine, again, our classroom. I know you've just been in there once or twice, but just any classroom, okay? And let's say there's 20 seats in the classroom, and there's 20 computers at those seats. Well, those are all part of the same local area network. Well, the way those devices talk to each other or share information is with their MAC address because they're on the same network. So MAC addresses are used within the local area network or the same network to communicate with each other. And so one thing I noticed someone said to routers and switches, and you're absolutely right, but one thing to keep in mind is that when it's a router, they're only communicating with its own default gateway. So remember, the default gateway is the entry and exit point for your total local area network. So if we had, like, let's say here's our router, here's our R1, okay, and then here's our switch. So the router is connected to the switch, and then the switch is connected to all these different PCs and the server, right? It's got all these connections. So let's say it's connected to 5 different computers or 20 different computers, like in the classroom. Each of these have a MAC address. These are all going to have their own MAC address. Okay? Right here, the router has a MAC address on its port right here because this is all part of the same local area network. So when PC1 over here needs to communicate to its default gateway, it uses the MAC address. Okay, if PC1 needs to communicate over here to PC2, it just goes through the switch and straight over to the PC. It never needs to go to the router if it's only talking to somebody else on its own network, okay? So again, remember, MAC addresses are used within the network for devices to talk to each other. And then the other part of your answer is absolutely right, to identify the devices. Every single device has its own MAC address. And things within your device have their own MAC address, and that is used to identify it. You're absolutely right. You're absolutely right. Okay, so the data link layer is divided into 2 sublayers. We had this answer earlier, so everybody entered into the chat box. What are the 2 sublayers? Send it directly to me. Yes, the LLC and the MAC sublayer, right? So the data link layer is divided into the LLC and the MAC sublayer. So look at this really carefully. So it falls between the physical layer and the network layer, okay? So the data link layer has this super important job. And if you remember, this is the area 2 where I said cybersecurity becomes really important around layer 2. So as the bits are coming off of the media, right? The media is like our cabling. It's coming off the media. The data link layer helps to pick those bits up off of the media, and then it pushes it to the LLC sublayer. The LLC sublayer gets it ready to move to the network layer, right? So it's like this intermediary. It has this super important job. Now, if we're going the other way on the OSI model, right? So now the packet's coming from the application, the presentation, the session, the transport. It hits the network layer. Well, the LLC sublayer helps bring the data from the packet down to the data link layer, the LLC layer. And then it gets it ready to go to the MAC sublayer. Now the MAC sublayer helps get it ready to put it down onto the media, to put it onto the Wi-Fi, put it onto the Bluetooth, put it onto the Ethernet cable, put it onto the fiber optic cable, whatever it is. So the data link layer, the reason it's sublayers is because it has so many jobs to do. Why didn't they just make it, 8-layer OSI model? I don't know, but they didn't. Okay, so the LLC, again, it's going to communicate with the network layer. Now see here, the network layer is layer 3. That's where IPv4 and IPv6 addressing happens, right? So the LLC is going to, as it's pulling it down, it's going to say, oh, okay, this is an IPv4 packet, or, oh, this is an IPv6 packet, okay? So it makes that determination as it's pulling it down. Now, if it's going the other way and it's pushing it up, the LLC sublayer, it does the same thing. It's like, okay, I can tell, like, this needs to go on an IPv4 network. So it's doing this, like, it's translating, kind of. Is it IPv4 or IPv6? So we can use IPv4 or IPv6, right? And it's going to add some control information. It's going to add some control information so that the packet can be delivered to the other side. Okay. Now remember, the name of the PDU at the network is the packet. What is the name of the PDU at the data link layer? Everybody answer. Everybody send me a message. What's the PDU at the data link layer? So the frame, it's called the frame. It's called the frame, okay? And the frame is going to get a destination MAC address and a source MAC address, okay? It's going to get a destination MAC address and a source MAC address. That way, it can communicate to its people, right? It can talk to its people on its same network. So again, now we're going to talk about the MAC sublayer. Remember, I said it helps to put the information onto the media or take the information off of the media. So notice it regulates the placement of the frames onto the media. It can communicate with wireless, Bluetooth, fiber optic, Ethernet. It doesn't care. It doesn't care. So that's another important thing about the data link layer. It really doesn't care what kind of media it is. Doesn't care what kind of media it is, okay? Let's see. This is where it's going to pick up the MAC addressing, the MAC right? The MAC sublayer. So the destination and the source. Now, something to keep in mind is that the destination MAC address goes into the frame first. Why does the destination MAC address go into the frame first instead of the source? So it's starting at the source, right? My computer, it's generating the frame. So why would the destination go in before the source? Why would the destination MAC address be listed in the frame before the source MAC address? Nobody has an answer for that one, huh? Okay, so definitely it does need to know where it's going. Okay, so it does need to know where it's going. So let's think about this like as from what we know about the internet. So with the internet, is a fast connection better than a slow connection? Yes, right? We can all agree. The faster I can communicate with you, the better. The faster one PC can communicate to its neighbor PC, the better. The reason the destination goes into the frame first is because of the way that frames get forwarded. So if you remember the term encapsulation and de-encapsulation, when it hits the data link layer, the data link layer needs to know, okay, where am I going to send this? Who is my neighbor that I'm going to send this to? So it opens up, it de-encapsulates, and it looks at the destination first because it reads it from left to right. And so as it reads the destination MAC address, it can immediately start to forward it. So putting the destination first just makes it go fast. That's all. It just makes it go fast. So building the MAC address table, that's not why the destination is in there first. The MAC address really looks at the port and then the MAC address. Okay, it looks at the port. But really the main reason the destination is first is speed. It's just so it's like, okay, I know where I'm going. Let me get you there. Have you ever, like, let's say you're going someplace and you knew the address, but you didn't have any idea how to get there. So because we have Google Maps now, did you just get in your car and start driving and you're like, okay, I'll figure it out let me get on the road so that I'm not late and I'll just start driving there and then I'll get the directions. It's kind of the same thing with these frames. It's like, let me just send it there. Let me just send it there. Okay. So that's why it's just a speed thing. Okay. And then lastly, the media access control will also do error detection, because what happens is, remember, it's either pulling it off the media or pushing it on the media. And what is on the media? Bits, ones and zeros, ones and zeros, ones and zeros, ones and zeros. Okay. So the way that error detection is done is it just counts the number of bits. So it'll say, there'll be a message that's like, okay, look, you're going to receive 1,640 bits. Okay. So because it's pulling and pushing the bits off and on the media, it's easy for it to do the error detection and just make sure it's got the right number of bits. Now, it can't tell if the bits are in the right order or if the bits were put on there right, but it can say, oh, I have 1,647 bits. Okay. So some of the standards that function at the data link layer, and these are important, you should write them down because they'll be on the CCNA and they're going to be on other tests. So Ethernet is described by the 802.3 standard. 802.3, that's just a standard that identifies and describes all the different things about Ethernet, how fast it has to be, what are the different speeds available, what does the cabling look like. Wi-Fi, which is 802.11, and Bluetooth, 802.15. The two most common ones that I see on the CCNA is the 802.3 and the 802.11. And you should write those down. If you already have them in your notes, that's awesome. Circle them. Okay. So the MAC sublayer controls the placement of the frames onto the media, just like traffic rules, right? Okay, you can get, like if you think about the freeway, the light turns green, okay, you can get on the freeway. The light is red, stop. Okay, green, you can get on it. Red, green, red, green. Okay, same thing. That's what the MAC sublayer does. Okay, so remember, for the data link layer, it doesn't care whether it's Wi-Fi, radio frequency, fiber optic, Ethernet. It doesn't care. It'll work no matter what. Okay, it regulates the placement. It doesn't care if it's putting it on fiber optic. It doesn't care if it's putting it on wireless. It doesn't care if it's putting it on an Ethernet copper cable. It doesn't care. Okay, all the different protocols can be used. It's totally media independent. It's media independent, okay? And it changes all along the way because, again, think about it. Like, I am on fiber optic. You might not be on fiber optic where you live, but you're still being able to get this signal, right? Okay. Network, yes. Okay, so, okay, yeah. So the way in which media is going to be accessed will depend upon the topology. Am I a hub and spoke? Am I a mesh network? Am I a point-to-point network? And then it's also going to depend upon, am I sharing this media? So in other words, like in our classroom, we're all on the same LAN. We're sharing media. Okay, we're sharing the media. Okay, so these two types of topologies are the most common topologies. Now you can see, or maybe you don't see, that is a typographical error where it says physical topology. Is there such thing as a physical topology? No. What is that? What kind of topology is that? Yeah, it's a physical topology, right? A physical topology. So again, it's a good idea to know the difference between the logical topologies and the physical topology. So a physical topology is the actual physicality of things. Where is it located? Is it in a router room? Is it in the basement? Is it in a phone closet? Is it in the 7th floor, right? It's the physical. And the logical is things like the IP addresses. It might be like, okay, this goes from our headquarters to our management office, from our management office to our side business, right? It tells the flow of the data, and it's not necessarily going to match up to the physical topology. Now, personally, what I see in industry a lot is a mashup of these things where a person, a company might actually have a physical topology, but then they also write all the IP addressing down and stuff like that. I mean, that makes a little bit more sense because then you can just have everything in one place. But here's an example of a logical topology. So notice here it's got our IP addresses. But again, physically, I can't really tell anything. Like it says department server, but is that in a different building? Is it its own router room? Is it even the same, is it on the same street? Who even knows, right? We don't even know. And then a physical topology, it's giving us a better description. See, look, this is telling us it's in the administrative offices, right? This is in the classroom. There's a hub in there. It just gives us a more physical, accurate depiction of the way our network is set up. Okay. Oh, this is a good question. Does the data link layer see the logical topology or does it see the physical topology? It's kind of a tricky question. Yep, I think you're right, Matthew. Right? So I think it sees the logical topology. It sees the logical, like it can't really detect anything about where something is located, but because it can look inside of the frame, it can see some of the addressing and it can see the media. So see, like here, it can see how this up here says Ethernet, right? It can tell whether or not it's on Ethernet, Wi-Fi. It can see MAC addresses, but it can't really tell like how far is this going? Where is this located? So if you could think of it like that, it sees the logical. Here's an example of some different topologies, right? Honestly, these are outdated, but you might get asked about them on a CCNA exam because sometimes companies will still have these older topologies in their building, even though it's not very common. Like we'll see a lot of bus topology, but you're not going to see a star topology. You're certainly never going to see a ring topology. Super ineffective. And when those devices are trying to talk to each other, they can collide and fight. So because we've added data link layer with switches, it's eliminated these types of topologies. And now we have full duplex communication. Okay. So WANs are going to be commonly connected using a point-to-point connection, hub and spoke, or mesh. Okay. So let's say like a bank wants to be connected directly to their financial servers. They might do a point-to-point connection. They want to have just one way in, one way out as fast as possible. Now this mesh network, what does that remind you of? And even the hub and spoke. If you think about as you're driving around the valley and you look up a little bit, what are some of the things you might see that looks like this hub and spoke topology? Maybe you've seen these, they look like trees, but they're not really trees. Anybody want to make a guess? Yeah, so this hub and spoke topology and or this full mesh topology is really common in a particular type of network that we see as we're driving around the valley. If you look up a little bit, you might see them around. And I said sometimes they look like a tree, but it's not really a tree. It just has been made to look like a tree. So how about cell towers for our mobile phones? Have you seen like the posts or trees that are cell towers, but they're made to look like trees? They work in a hub and spoke or in this full mesh topology. Cell towers, this is the layout for cell towers. Yes, like the fake palm trees, exactly right. You know, sometimes they're fake palm trees. I've seen like the fake pine trees. And sometimes they just, it's just a pole and it's got like boxes around it, things that look like, yeah. Yeah, they're not necessarily just 5G towers. They could be the regular old fashioned, So the 5G towers, what makes them special is they're set up. Oh, now you'll probably see them because we're telling you about them. The 5G networks are set up as full mesh and they're set up close together. That's what allows the speed. That's what allows the speed. Yeah, so if you look in the valley, here, I'll show you. Let's see. Give me a second here. They're all over the Phoenix area. See, you may not, I mean, you may not know that you've seen one because they look so much like a real palm tree. So, like, here's a picture of a good one. See that? That's actually a cell phone tower. Cell tower cactus in Arizona. They have spruce trees. So see, look, that's a cell tower right there. Yeah, and again, see how here you can see, here's the modules. See those modules in there? Okay, so look at that, and then, you know, take a look at this picture. Right? So take a look at this. Let's see, where did it go? Take a look at that picture. See that? Cell tower. And then when you if you take and you interlace these, then it becomes full mesh. And so what they'll do is they'll put a lot of these close to each other so that they can get a full mesh topology. That's how they're getting 5G. That's how 5G has to be set up. Yeah, right. Okay, let's see. Okay, so if you notice here, this is talking about the data link layer and what the interaction with our router is. So you remember I said a router is actually a layer 3 device, okay? However, it does have to do some layer 2 functioning because it's receiving MAC addresses. It's receiving MAC addresses, right? Because it's part of the default gateway is part of our local area network. So each hop along a path, a router will perform some layer 2 functions, even though it's a layer 3 device. Okay, so first of all, it's going to accept the frame from the switch. It's going to take the frame from the switch. It's going to open it up, it's going to de-encapsulate it, and it's going to look inside to see where it's got to send this frame. After it's done that, it repackages it. Because remember, you can't just send raw data across the internet. It's got to be in a PDU. It has to be in the format of the PDU. Okay? After it figures that out from the de-encapsulation and the encapsulation, then it will do its networking job and it will forward it. It will forward it. So a router does have a little bit of layer 2 functionality. So that's why we need the LLC layer in the data link layer, because it's got to communicate with the layer 3 device. Okay? Okay, a network that shares a common medium with multiple nodes is called what? Multi-access network, a WAN network, a LAN network, or an NBMA network. So a network that shares a common media. I've only got one answer. Yes, Pedro, that's right. Okay, so we're going to break this question down because one of the things I want you guys to get good at and practice doing is how to, what I call muscle brain these questions. Because what's going to end up happening when you take the CCNA exam is it doesn't matter how hard you study, there's still going to be some questions that you're like, what? And so you want to be able to start breaking these questions down so that you can make a good educated guess. So first of all, what is a node referring to? Like what a node is another word for what in our networking world? A node is another word for what? Yeah, Francisco, you're absolutely right. It's another word for a device. Okay, so it says here a network that shares a common medium with multiple nodes. Okay, so let's here's a device. So this is my best attempt at drawing some computers, okay? So these are all computers, you guys. Computers, okay. Now, so that's what our nodes are. It says we have multiple nodes. A network that shares a common medium. So what is the common medium referring to? Medium is referring to what? Yes, Luis, you're right. So let me get a couple more answers. At this point, you guys, we've used this terminology a dozen times. Everyone should be able to tell me what this means. Medium. What is, when I say the word media or medium in networking terminology, what am I referring to? I'm going to wait for everybody to give me an answer. Yes, Damien, exactly right. Yes, Pedro. Yes, Aaron. Matthew, can you be more specific? Yes, Francisco. You're on the right track. Okay, so once again, I'm going to say you need to write this down. If you don't know this inside and out already, because we've used the terminology a lot, I really want you to get this because it's important to know this terminology because you're going to use it throughout your whole career, and you're also going to use it on the CCNA and any exams and stuff like that, okay? So again, my thought is that everyone would just know right off the top of their head what media is or medium is because we've used the term so much. So if you don't know this, and even if you do know this, I want you to write this down, okay? Media refers to the cables, the Wi-Fi, like the radio frequency, the fiber optic cables. Media refers to whatever is carrying the bits, right? Whatever is carrying the bits. So if I ever use the word, what medium are you using to connect your two routers? Then I'm asking you, are you using Ethernet? Are you using fiber optic? Are they going to be connected with wireless? Or if I say, hey, the media I want you to use is light, then you should be able to, oh, the media she wants me to use is light, so I got to use fiber optic. Okay, so once again, this is something that I need you to write down. I would write it down even if you know it. I'm going to have you guys turn your notes in tonight, okay? So now we've got this multiple nodes. We've got the media, so let's just say it's Ethernet, okay? Let's say it's Ethernet. So here's my media, and I've got all of these connected. Okay, so I've got all of these connected. That kind of looks like a worm. You know what I mean, though. Okay, so now let's ask this question. A network that shares a common media with multiple nodes. Now let's say these are all trying to get out to the internet, okay? So now, what is your answer? So I can see why you might think it's a LAN, right? But it's not. Yeah, in this case, this is a multi-access network. Multiple devices need to access the media and get out to the internet. Now, again, a LAN network, this is kind of a tricky question because these are all on a LAN, right? But this key here is a network that shares a common media. That's what tells me it's the multi-access. Now, a WAN is usually like, let's say I'm going to connect one ISP to a large business. And a WAN is just one way in and one way out. So there's usually just one access point. It's not multiple access points. Now, NBMA, you've got to know what the NB stands for, okay? The NB actually stands for non-broadcast. Yes, yeah, the LAN would work without the internet. Yeah. And actually, I think if it were a LAN, we would probably need to have some extra words inside of here. So that's why, again, this one could be a little confusing. But NBMA means a non-broadcast network. Well, whenever we have multiple nodes all on the same Ethernet, they're going to be able to broadcast to each other. They're going to be able to broadcast to each other. Hint, Ethernet LANs and WLANs are examples. So I think this is a good hint. So this is actually telling us that a LAN is a multi-access network. So that maybe explains a little bit better why the answer isn't a LAN. It's because a LAN is a multi-access network. And a wireless LAN, so again, think about if you go on campus, might be a good example. When you go on campus, there's wireless access points and you can get onto the wireless network. And so all of us, we're multiple devices are getting onto the wireless network. Okay, so there's our little picture. Okay. Yes. Okay, let me keep going. So some multi-access networks require rules to dictate how we're going to get onto the network, okay? Because again, if all of these devices are trying to talk at the same time or if they have different types of messages, there might have to be some regulations about how they're going to do that. Well, there's something called contention-based and controlled access. Okay, so there's two different ways, contention-based and controlled access. Now, contention-based is the way that everything used to be because we didn't have switches. We didn't have really efficient use of switches. And so any of these devices would just be like, I need to send a message. No, I need to send a message, but I want to send a message. No, I need to send a message. So literally there was lots of disconnections and drop-offs, and the internet of old, like even 20 years ago, just wasn't as efficient and wasn't as it didn't have the same quality because there was this contention for the network. Well, now that we've added switches, we have full duplex, and so the internet traffic and data traffic can go in two different directions at the same time without interfering and getting in each other's way. So we no longer really deal with contention-based networks when it comes to LANs. Now, with wireless LANs, we still have a problem. Come on, go away. Hold on, I'm trying to get this thing to go away. Go away. Why is that not going away? Hold on. Okay. I don't know how to make it go away there. Now it just went away. Okay. So the two contention-based media access control methods are used in a multi-access network. So remember, multi-access network is when we have multiple devices getting onto the media. Okay, wireless is a type of multi-access. So with contention-based, we have collision detection and collision avoidance. Okay, again, this collision detection, we don't really deal with it anymore because we don't have half duplex. We have everything in full duplex. Okay, now with collision avoidance, what it's doing is it's looking down at the media and it's kind of waiting its turn. It's like going to see, well, I want to try to avoid a collision. Okay, and so I'm going to just make sure that when I send data, there's no other data being sent. Now, if you look at this collision avoidance, notice it's 802.11. So that's wireless. That is the wireless, okay? So the way that wireless works is collision avoidance. That's why sometimes, have any of you ever been on your wireless phone and you might get dropped or you get interference? And then it'll come back? Well, the reason is because it's wireless functions using this contention-based type of talking to each other. And it's called collision avoidance. And it's got like a timing mechanism. So basically, before a wireless makes a connection, it'll say, hey, it's going to talk to the media. And it's basically going to say out to the media network, I need to establish a connection. And I'm going to need 3 milliseconds to do that. Okay, so for 3 milliseconds, can all of you on the same network just stay off the network while I make this connection? And the other devices, they just stay off it. They wait 3 milliseconds and then they start. If the wireless device didn't get its work done in those 3 milliseconds, then there could be a collision. And sometimes when we're on our cell phones, that happens. We get that little collision. Okay. So let's see. So also known as scheduled access. This is a legacy method. It's really inefficient. You might have to know it, but it's not very, again, so it's not used anymore. So we're going to pass by this. But you do want to know for sure the wireless, right? The wireless contention-based collision avoidance. So you want to write that down. Contention-based. It's fighting for the media, and the way it's going to do that is it's going to try to avoid having a collision. So again, notice here it says, I want to avoid a collision. I need to send this frame, and I think it's going to take me 2.5 seconds to send the frame. So hey, everybody that's out on this wireless network, can you just stay off of it for 2.5 seconds? All of the other wireless devices receive the message. And they're like, oh, okay, I'll just wait 2.5 seconds. Okay. Now again, because we've introduced layer 2 devices, switches, we don't have that problem anymore on Ethernet actual networks. If we've got everything wired up with Ethernet, we don't have that problem. So now that we've introduced switches, I can send data and receive data all at the same time. So what is that called? Everybody answer in the box. What is that called when I can send and receive at the same time? Yeah, it's full duplex. It's working in 2 ways. It's full duplex. Okay, it's sending and receiving at the same time. Now, when switches came into our world, that's when things really got fast, right? That's when things really started to get fast for us. Half duplex is if something is just going one direction. Now, interestingly enough, if your network has accidentally been set to half duplex, it will still work, but you're going to get drops, because you're going to have all these collisions, okay? You're going to have all these collisions. Now, again, remember what I said is that when you have a local area network, how do the devices on the local area network actually talk to each other and share information? What are they using to talk to each other and share information? Yes. Yes, Oscar, that's right. Everybody answer. So if A, B, C, D, E, how are they talking to each other? Nope, not that one, Luis, a different one. We're talking about layer 2. Layer 2. Pedro, what's inside the frame? Okay, so again, this slide says the answer right here, right? The layer 2 address. So what is the layer 2 address referring to? Okay, so again, this is something to write down. When you're on a LAN, right? When you're on layer 2, these devices, they use their MAC addresses to talk to each other. They use their MAC addresses. So if you remember on Monday, we did that demonstration with the MAC address table. So remember, it's going to match up the port number to the MAC address so that it knows how to forward the frames so that these devices can all talk to each other. Okay, yeah, it's Damien, it's also called a physical address. So these can be called MAC addresses, physical addresses, layer 2 addresses, and there was some other name that we said. What's the other name that it could be called? Yeah, exactly right. It can be called the burned in address, a BIA. And the reason they call it a BIA is because that is stored in ROM. So it cannot be changed because it's in permanent memory. It's in permanent memory. So you'll see that most devices will have a BIA and a MAC address. They're exactly the same thing. It's just that a BIA can never be spoofed. It can't be faked. But the MAC address that gets stored in RAM, it can actually be faked. It can be faked, which again is why the cybersecurity at layer 2 is so important. Okay, so if these guys are talking to each other, they have to have a MAC address and they use the MAC address to talk to each other. Okay, now let's take a look at this. This is a multi-access topology. So let's take a look at this point-to-point topology. Okay, we're going to take a look at this point-to-point topology. So this is like a router talking to another router. And notice there's just one way in and one way out. They're just going back and forth. There aren't all of these multiple access points. There's one way in, there's one way out. One way in, one way out. There's no place else for it to go. In this case, it doesn't care what the MAC address is because if it receives a frame, right? So if this router receives a frame, well, there's only one place to send it, and that's this direction. So it doesn't even look at the MAC address. Same goes here. If this one gets a frame, there's only one way to send it. It doesn't even look at the MAC address. So that's why a MAC address is important on a multi-access network. But on a point-to-point network, it's not important. It's not important on a point-to-point network. Okay? There's only one way in, one way out. It just doesn't care about the frame. Okay, again, we've already talked about these standards. These are some important ones, the 802.3, 802.11. This 802.4, old-fashioned, 802.5, token ring, we don't care about that. Okay, these are the different organizations that manage these standards. The important one for you to know is the IEEE. The IEEE, that's doing Ethernet. Okay, let's see. So what carries information about the media? So what is carrying information about the media? Yes, Aaron. Yep, yes. What is carrying information about the media? So I'm going to give you a hint. So remember there's a certain layer that has to look at the media and put it down onto the media and pick it up off the media. So what layer of the OSI model is that? And then in turn, if you know what the layer of the OSI model is, you can tell what the PDU is, right? So it is the frame, because if we think about the OSI model, layer 2, that's the data link layer. That's where switches do all the work, right? And the MAC, right, the sub layer, the media access control layer, it helps to control what goes on to the media and what comes off the media. And all of that's being done inside the frame. The frame has that information. So the frame is going to have the destination MAC address, the source MAC address. The frame is also going to have what type of media it is. It's going to know, is it Wi-Fi? Like, is it radio frequency? Is it Ethernet? It's going to know if it's fiber optic. It's going to know if it's light. The frame is, if you think of it kind of like an envelope, it contains all this information inside of it, okay? It's got error detection. Remember I said it counts the number of bits. Did I get the right number of bits? Okay, so we're going to look at the 3 basic parts of a frame, okay? So this is like a data link frame. So this is what gets encapsulated and de-encapsulated. So here's our header, right? So these first 4 segments are part of the header, the frame start. It's like, okay, hey, a frame's going to come, okay? And then also remember we said here, everything's all chopped up, right? It's all chopped up. So in the frame start, we're also going to have, this is segment number 1. This is the first piece of chopped up information, or it's the second piece of chopped up information, or the third piece of chopped up information. And we've got addressing. This is our source and destination MAC addressing. And remember, the destination goes first. The type. The type is referring to the network layer type. Is it IPv4? Is it IPv6? Okay. And then the control. Now the control is a couple of different things, but it's how we're going to control what we put onto the media. So it's like the timing. Now they're giving an example of QoS, but we don't really deal with QoS at this point. The data is everything that's coming down. So it's going to have everything inside of it from the upper layers. Everything from the application, the presentation, the session, the transport, and the network layer. It's all just wrapped up. The error detection, right? It's counting the number of bits. And then last, the frame stop. Okay, it's time to stop. Okay, this is an example of an Ethernet frame. Here's something else the CCNA is going to want you to know about the Ethernet frame. And we're going to talk about it again a lot on Monday. And we're going to fill out some forms and do some practicing. Okay. So what's something that a wireless frame has that an Ethernet frame wouldn't have? So what's something that a wireless frame would have that a Ethernet frame would not have? Everyone answer. So think about what wireless has to do to use the media. We haven't talked about encryption, so it's something we've talked about. So remember, when wireless needs to use the media, it has to do something special so that it doesn't have collisions. And it's something we've already talked about in previous slides today. So it's going to be, this is contention-based, and it does collision avoidance, absolutely right. In order to avoid collision, it does something. It tells the network something so that it can reserve the media. What does it do to reserve the media? How does it reserve the media? Let's see, it tells the network to disconnect. No, you're on the right track, but it doesn't tell them to disconnect. It tells them something else. Okay, this is where we talked about it. So a frame that's going to use wireless needs to have something else inside of the header, inside of the frame. What does it need to have? So that's right. Does this page give you guys a hint? It does sense and listen. Okay, so is everybody here? What it does is it tells everybody, hey, I'm going to need the media in this example for 2.5 seconds. Now that's probably more like milliseconds, okay? So inside the wireless header, it's going to have a timing mechanism for how much time it needs to reserve the media. So inside of a wireless frame, if it's going to have a time, how much time. Okay, so inside of the frame, it can be different depending upon the media that it needs, okay? Depending upon the media. So it's going to have a destination and a source MAC address, always. And then if it's wireless, the wireless is also going to have a timing mechanism, a duration. See, check this out right here. Duration. It's saying, hey, I need to use the media for 2.5 milliseconds. Okay. All of them will have a frame check sequence and a stop. All of them will have a frame stop. Let's see. So this is saying how long it needs to use the media. Let me look here. We'll do this one on Monday. Let me look and see where we're at. Oh, we're good. Okay. So what we're going to do on Monday is we're going to talk about Module 7 and Module 9. Module 9 is really short, they're related because remember we're doing 6, 7, and 9. We're skipping 8 for right now. We're going to do 8 next week, like the weekend. Next week. So make sure that on Monday, you're ready to talk about Module 6, 7, and 9. They're all related. Okay? They're all related. So again, practice the format of an Ethernet frame. You wanted the MAC address. We're going to talk more about the MAC address table. Now, we already talked about the MAC address table, so we'll review that again. The different forwarding methods. We're going to review the data link sublayers, encapsulation and de-encapsulation, error detection. So these are the important things for Module 7. How a frame is processed. What is a unicast, a multicast, and a broadcast? Now, in Module 6, 7, and 9, in those modules, they've got really good videos. I strongly recommend you watch them because they do a really, really good job of helping you understand how a switch works and how and what happens at layer 2. So if you want to get a good understanding of that, review those videos. Okay, review those videos. And okay, so I want you to go ahead and take a picture of your notes that you took today during class. And that's going to be in week 4. Yeah, only the wireless has the timer, Christian. That's a good question. That is a good question. Let's see. You know, it's not a protocol. It's the duration is in the header. I'll show you that picture again. I'll show you. It's actually like it'll list the wireless device will be like, okay, I think I need to use the wireless to open up just to get the session going. So it doesn't, if you're going to have a 20-minute conversation, it doesn't hold it open for 20 minutes. It's just to make the connection, okay? And again, it's in milliseconds. So it might be like, I need to make this connection using 10 milliseconds. Or 255 milliseconds if it's a further distance. And so that's how long it will ask the other devices on the network to stay off of it. I'm going to bring that picture back up and I'll show you. So right here under week 4, class activities, network addressing and module 6 notes. Is this it, Leslie? Yes, that's it, right? So take a picture. Apps, that's exactly right. That's exactly right. That is why a wired connection is better. And why you could have problems on the wireless. Like, see, even though I'm on my laptop, I'm wired up with my Ethernet cable. So right here is where you're uploading your notes from today. And again, these are notes that you took today during class. And let's see, I'm going to show, let me show this again. So it's not exactly a protocol, it's a spot in the header. So it's like a spot in the frame. So here is our wireless frame, right? And so this first part here is all part of the header. And within the header is the duration. And then here is the destination MAC address. Here's the source MAC address. Okay. All of these things, we don't really need to know all these other little things in here. The important thing is to know that a wireless frame has a duration in it. That's what makes it different. Yeah. So, you know, a DOS attack works in lots. There's a couple of different ways. It's one of the ways is it ties up. So there is a way to use the wireless to tie up and do a denial of service by holding open everything, right? So it's constantly making requests. I need the network. I need the network. I need the media. I need the media, so that nothing else can ever get on it. So that is one way that it's done on a wireless network. Yes, there's other ways too. ARP requests, MAC requests. I mean, there's all different ways, but one way is tying up the media with a timing request. That's not the only reason that Wi-Fi is slower. There's just a limitation to the bandwidth of Wi-Fi. There's just so much that you can get. And again, like with 5G, I believe that the reason that that is faster is because of the way they're meshing the 5G network. I don't understand it completely, but I believe that's why. Okay, once you upload your notes, you're free to go. Okay, now you take advantage, please, of this week, you know, because again, we're really digging into the meat of networking now. So I know it's getting a little harder because we're having to understand stuff. you really want to work on the terminology. And then next week, we're going to learn about network address ranges. And we're going to spend the whole week talking about network address ranges, okay? So we'll do that. So please make sure you watch that video because, again, it's starting to, our network addressing is getting a little bit harder, right? Just a little bit harder. So watch that. I hope to see some of you tomorrow on campus. Again, I'll be getting on campus tomorrow at about 2 o'clock. I do have a meeting from about 2:30 to 3 o'clock that I won't be available, but I will be there to talk to people, help people. We've got a tutor coming in at 3 o'clock. Okay. Yes, okay, so the lab is going to be open at 2 o'clock. Someone will be there to help you at 3 o'clock. You can stay until we leave at 9 or 9:30, okay? You just can't be in my classroom because I have a class from 6 to 9. But we'll put you someplace else. So you literally could stay until 9:30 tomorrow and work, okay? So again, if you look at the home page, okay, if you look at the home page, it will give you all of the hours. So tomorrow is Thursday, so 3 o'clock until 9 o'clock. And again, Leslie and I usually leave at about 9:30. We don't want to stay past 9:30 if we can avoid it. But if you guys are coming to work, please, you know, there's a lot of distractions at home. It sometimes is just easier to go to school and just be someplace that is school. So, you know, you don't have kids and family and pets and noise and parking lots and all that stuff. Come to school. This will really help you get ahead. Plus, there's a tutor there to help you. Leslie's there to help you. I'm teaching, so it's hard for me to help very much, but while I'm teaching, but 3 to 9, please come to campus tomorrow. Yeah, come at 3. You know, David came yesterday at I guess he got there about 3 o'clock. Yeah, you could come earlier. The only problem is if you need help setting up a lab, we don't actually have somebody there unless I get there at 2 and can help you. Okay.